And this delta, it's used to describe the state transition rules. Okay? Remember what they are again? It's a rule that decides what the next state is, given two things: the current state and the symbol being read at the moment. Right? So this delta, if you like, is a function, and it maps a combination of two things: the current state and the current symbol being read, if you like, in the stream. Okay. So, for example, say in your state diagram, you have a state X and a transition with a 1 labeled 1 and a state Y. So this transition, it's in state X. Current state is X. It's reading symbol 1. And therefore, with these two things, if you're in state X and you're reading symbol 1, then your next state is Y. Okay? So your delta is a function with two arguments, two parameters, X and 1. Your output will be Y. Okay? So look at it as a function with two parameters: the current state, the symbol being read, and the output of this function is the next state, Y. Right? So that's what this delta is. It's a transition function. So this is a mathematical way of describing the state transition table. Okay? Right? It's a kind of mathematical shorthand, but it's quite precise. All right. So now we can actually now that we're going to use the transition function delta to describe the state transition table, we can now write out in formal terms the definition. So in the text it's called definition 1.5. Okay? So a finite automaton is a 5-tuple. This list of 5 things. Q, capital Q, capital sigma, delta, Q naught, and capital F. Now these are just labels for the 5 things. So capital Q, that represents the set of states in your automaton. Okay. Capital sigma, we've done that before. That represents the language of input symbols. Okay. Delta, well, we just talked about that. That's your transition function. It'll take one of these states and one of these symbols and map it like this into the next state. Okay. Q naught, that's your start state, whatever it is, and F, capital F, that's your set of accept states. Right? So you see this 5-tuple. That gives you a complete description of your automaton. Complete description? Doesn't tell you what its function is. Debatable. Okay. Anyway, that's the formal definition of an automaton. Now, from this, you can probably work out what its function is. Probably certainly. Okay. All right. So summarising just quickly again, that there are a few more details. So Q is the finite set. It's a finite set. It's called the states. So it's just a list. It's a set of all the states in the automaton. Sigma, that's also a finite set. It's called the alphabet, right? So capital sigma is the alphabet. In other words, the set of allowed symbols in your input stream. Okay. The third thing is delta, the transition function. Now it's a function, right? So it has a domain and a range. Remember that from set theory in chapter 0? So the domain, the starting set, right, and the output set, if you like. The from set to the to set. So it maps an element of this set it maps an element of the domain to an element in the range. And these are two sets, like the starting set, the from set, and the to set. Okay. Now, why is this written here in the form of a Cartesian product? Well, remember, what is a Cartesian product? Right? It's an ordered pair, x comma y. X is a member of. Well, you have a Cartesian product of two sets, A and B. So A cross B. So it's often called the cross product as well, Cartesian product. And a Cartesian product, by definition, remember from chapter 0, previous chapter, it's the set of all ordered pairs of x comma y, with in parentheses, x comma y. X is a member of set A, and y is a member of set B. And it's all possible ordered pairs, x comma y. Well, that's what this is. So for each state, and for a given member of your alphabet, in other words, for a given input symbol, okay? So for each possible pair like this, there will be a decision. That's what delta does. It maps that pair into the next state, which is a member of Q, of course. So here it is in set notation, right? This is your domain, this is your range, and this is the function. That's what a function does, right? A function is a mapper. A function takes an element of your domain, the domain set, and maps it to a member of your range set. Okay? So more intuitively, your delta is a transition function, and it maps a combination of the current state and the input signal currently being read. So it's one of these ordered pairs, right, of all possible, and maps that ordered pair into the next state, which will be some state, and that'll be a member of Q. Okay, so that's probably the hardest part so far. But it's precise. It's in mathematical terms. Cartesian product. Okay, so the elements of Cartesian product are an ordered pair, and it's that ordered pair that's important. So the first term in your ordered pair is the current state. The second term in your ordered pair is the current symbol being read. Okay? And it maps that ordered pair into the next state, which is a member of your set of states. Right? You can't see it. So, well, 4 and 5, pretty easy. So, Q0 belongs to big Q. Right? So you have to list the start state, and there's only one of them. Right? So that answers that question. Oh, wait a minute. Yeah, there's only one of them, so you have to have a start state. Okay? And 5 is F is a subset of Q. Right? And F, remember, is the set of accept states. Right? Well, I'll just continue on to the next session.